We will start in 1 minute. Today we'll be in section 1110. We'll be discussing the famous Taylor and Maclaurin series. But first, recall how a power series representation of 1 over 1 minus x can be found by long division. The denominator 1 minus x, we divide that into the numerator. 1 goes into 1 one time. Then multiply 1 times the divisor, and we get 1 minus x. And then we subtract. 1 minus 1 is 0. 0 minus negative x is x. And then we start the cycle over again. 1 goes into x times. Then x times the divisor is x minus x squared. And then we subtract. X minus x is 0. 0 minus negative x squared is 0 plus x squared, or x squared. And then 1 goes into x squared times. And then x squared times the divisor, x squared minus x to the third, and so on. So, as Providence would have it, we ran out of space, so we'll just write 1 over 1 minus x equals the infinite series 1 plus x squared plus x to the third, and so on. And in sigma notation, starting at n equals 0, going to infinity, the terms are x to the n. And this converges for absolute value of x less than 1. So if you remember, this is just a geometric series. And if the common ratio is between -1 and 1, then the sum of that geometric series is, in this case, 1 over 1 minus x. As we have seen, the power series representation of a basic rational function can be used to find power series representations of more complicated functions. So, such as this rational function, 1 over 1 minus x, we use this to find power series representations for a bunch of other functions. In this section, section 1110, we will expand our knowledge by learning how to find power series representations of a few familiar functions, which can then be used to find power series representations of even more complex functions. So a note, There do exist functions that do not have power series representations. But if a function does have a power series representation, then that power series can be found. So we begin here by supposing that a function f can be represented by a power series at A, or sometimes we say it can be represented by a power series about A. Well, if that is the case, then f of x is equal to this power series. The terms are c sub n times x minus a to the n starts at 0. And then when we expand this a few steps, we get c sub 0 plus c sub 1 times the binomial x minus a, and so on. And this is for the absolute value of x minus a less than the radius of convergence. So the radius of convergence can be anywhere from 0 to infinity, depending upon the function. Okay, so our first note, since f of x is equal to this power series, when we evaluate the function f at x equals a, all of the binomials are 0. If you replace x with a minus a is 0. And so the only term that's left is c sub 0. So f of a is equal to c sub 0. That's the constant in the power series. Then if we compute the first derivative, f prime of x of the power series, well, the constant c sub 0 goes to 0 when we take the derivative of that. And then we're just left with c sub 1 plus 2 times c sub 2 times x minus a plus 3 times c sub 3 times x minus a to the second, and so on. And then if we evaluate the first derivative when x equals a, we just have c sub 1, which is the coefficient of the x minus a in the original power series. So f prime of a is equal to c sub 1. When we compute the second derivative, we get these terms, 2 times c sub 2 plus 3 times 2 times c sub 3 times x minus a plus 4 times 3 times c sub 4 times the binomial x minus a squared, and so on. So note that when we evaluate the second derivative at x equals a, all of the terms are 0 except 2 times c sub 2. And so the coefficient c sub 2 is just the second derivative of f evaluated at a divided by 2. Okay, we'll do one more derivative. The third derivative of f, we just take the derivatives term by term. This time we get 3 times 2 times c sub 3 plus 4 times 3 times 2 times c sub 4 times the binomial x minus a, and then plus 5 times 4 times 3 times c sub 5 times the binomial x minus a to the second, and so on. So if we evaluate the third derivative, of f at x equals a. There's only one term that isn't 0. All of the terms with the binomial x minus a are 0 when x is a. And so the third derivative of a is equal to 3 times 2 times c sub 3. So when we solve for the coefficient c sub 3, we just get the third derivative of f evaluated at a divided by 3 times 2. Okay, so this exercise gets tedious really fast, and I'll refer you to page 759. But if we continue this process by taking more and more derivatives, then it turns out that the coefficient c sub n for the power series is the nth derivative of f evaluated at a divided by n factorial. So just a note, c sub n is the coefficient one of the coefficients, or it's the general coefficient for the power series. So this is kind of a nice formula for the coefficients of a function that can be represented by a power series at a. Okay, on the next page, a couple of notes regarding notation. The nth derivative of f of x is denoted by this notation. So in parentheses, we have n. So this means the nth derivative of f. And so it makes sense that the zeroth, is that a word? The zeroth derivative of f is just the function itself, because we're not actually taking a derivative. So this is handy notation when we're writing out the sigma notation for a power series representation. And we also adopt the convention that 0 factorial equals 1. So in combinatorics, if you've ever studied combinatorics, you learn that just by definition, 0 factorial is understood to be 1. It doesn't cause any problems, and it works nicely with the other factorial formulas. Okay, that brings us to Theorem 5. If f has a power series representation at x equals a, that is, if f of x is equal to this infinite series where the terms are c sub n times x minus a to the n, as n goes from 0 to infinity, then for the absolute value of x minus a less than the radius of convergence r, then the coefficients are given by c sub n equals the nth derivative of f evaluated at a divided by n factorial. So this is what we concluded on the previous page, the coefficients of the power series representation of f at x equals a. This power series in Theorem 5 is called the Taylor series of the function f at a. So more explicitly, the Taylor series of f at a, if you expand it, it looks like this. F of a, I could have put, we divide this by 0 factorial, but it's okay. Since 0 factorial equals 1, f of a plus the first derivative, first derivative of f evaluated at a divided by 1 factorial times x minus a to the first, and so on. Okay, another series is called the Maclaurin series. The Maclaurin series is just the Taylor series when a is 0. So the notation for the Maclaurin series, all we do is go up to the Taylor series and replace every a with 0. So the Maclaurin series is f of 0 plus the first derivative of f evaluated at 0 divided by 1 factorial times x, and then plus the second derivative of f evaluated at 0 divided by 2 factorial times x squared, and so on. And here's the sigma notation for the Maclaurin series of the function f. Okay, a function that we work with and see quite often is f of x equals e to the x, sometimes just referred to as the exponential function. So let's find the Maclaurin series for f of x equals e to the x. Well, f of x is e to the x. So this is like having the 0th derivative. And then when we evaluate that at 0, we get e to the 0, which is just 1. Then the first derivative of f, first derivative of e to the x is also e to the x. And so if we evaluate the first derivative at x equals 0, we get e to the 0 or 1 again. So you know that in general, for f of x equals e to the x, the nth derivative is just e to the x. And so the nth derivative evaluated at 0 is equal to 1 in this case. All right, so the Maclaurin series for f of x equals e to the x is, let's see, f of 0 is 1 plus the first derivative of f evaluated at 0 divided by 1. So that's 1 and then times x. And then plus the second derivative of f evaluated at 0 divided by 2 factorial times x squared. So 1 divided by 2 factorial times x squared. Well, you see the pattern. The third derivative of f evaluated at 0 is 1 again. This time it's 1 divided by 3 factorial times x to the third. and so on. So I'll rewrite this as 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the third over 3 factorial, and so on. And so in sigma notation, the Maclaurin series for f of x equals e to the x, if we start at n equals 0, we can write x to the n over n factorial. Okay, that is the Maclaurin series for e to the x. I remember the statement earlier that not every function is equal to its Taylor series. So we can't say yet that this is what e to the x is equal to. We have to look at some other stuff first. But anyway, this is the Maclaurin series for e to the x, or you could also call it the Taylor series at a equals 0. So I'll just make a note, make sure this is one of the Maclaurin series that you'll want to remember. So know this one, or remember it. Okay, on the next page, according to Theorem 5 on page 760, if a function has a power series representation at x equals a, then f of x is equal to the Taylor series at x equals a. So this is what we saw on the previous pages. So the question is, how is it determined if a function is equal to its Taylor series? Or Maclaurin series, since a Maclaurin series is just a special case of a Taylor series. Before answering that question, more definitions are needed. The nth partial sum of the Taylor series of a function f at a is denoted by t sub n of x. We have discussed sequences of partial sums before in section 11.2. Sequences of partial sums are addressed for the first time there. So you can review that if it helps see the sequence of partial sums. Okay. The nth partial sum of the Taylor series, denoted by t sub n of x, is also called the nth degree Taylor polynomial of the function f at a. So using sigma notation, t sub n of x is the sum from I equals 0 to n. And the terms are the ith derivative of f evaluated at a divided by I factorial times x minus a to the I. Note that the number of terms in the Taylor polynomial is a finite number. At most, there are n plus 1 terms. So if you were to expand this, the first term would be the function f evaluated at a. Then the second term, the first derivative of f evaluated at a divided by 1 factorial times x minus a to the first. Then the second derivative of f evaluated at a divided by 2 factorial times x minus a to the second, and so on. The last term for the nth degree Taylor polynomial is the nth derivative of f evaluated at a divided by n factorial times x minus a to the n. Moving in the wrong direction. Okay. So it's a polynomial of degree n. Okay, now let f be a function whose nth degree Taylor polynomial at a is t sub n of x as defined above. Then there exists a function capital R sub n of x such that f of x is equal to t sub n of x plus R sub n of x. The function R sub n of x is called the remainder of the Taylor series of f at a. Earlier on in chapter 11, we saw remainders of series. So this is just the remainder of a Taylor series. All right, so what must be true if a function f is equal to its Taylor series at a? Well, analogous to what we discussed in section 11.2, it must be the case that f of x is equal to the limit of the Taylor polynomials, t sub n of x, as n approaches infinity. So if f is equal to its Taylor series at a, then f of x is equal to the limit of the Taylor polynomials. So I'll just rewrite that again. If f is equal to its Taylor series at a, then f of x is equal to the limit of the Taylor polynomials as n goes to infinity. Well, since f of x equals the nth degree Taylor polynomial, t sub n of x, plus the remainder R sub n of x, it must be the case it must be the case that the limit of the remainder is equal to 0. If the limit of the nth degree Taylor polynomials equals f of x. So we discussed this concept in section 11.2. When we had a series that was equal to the first n terms plus the remainder, then the series converges when the remainder goes to 0 as n goes to infinity. So once again, you can see section 11.2 for a refresher on that. Okay, so this discussion is basically what the next theorem says, Theorem 8. Hey, Theorem 8, if f of x is equal to t sub n of x plus r sub n of x, where t sub n is the nth degree Taylor polynomial of f at x equals a, and if the limit of the remainder r sub n of x as n goes to infinity is equal to 0, for the absolute value of x minus a less than the interval of convergence or the radius of convergence, capital R, then f is equal to the sum of its Taylor series on the same interval. And so the next question is how to determine when the limit of the remainder r sub n of x is equal to 0. Taylor's inequality on page 762 answers that question. So Taylor's inequality, it's just a theorem. If the absolute value of the n plus first derivative of f evaluated at x is less than or equal to m, for the absolute value of x minus a less than or equal to d, then the remainder, r sub n of x of the Taylor series satisfies this inequality. The absolute value of r sub n of x is less than or equal to m divided by n plus 1 factorial times the absolute value of x minus a to the n plus first for the absolute value of x minus a less than or equal to d. So if we show that if the absolute value of r sub n of x, if that's less than or equal to m over n plus 1 factorial times x minus a, the absolute value of x minus a to the n plus 1, for the absolute value of x minus a less than or equal to d, then the limit of the absolute value of the remainder r sub n of x is equal to 0. And we saw earlier this semester that if the limit of the absolute value of a sequence is 0, then the limit of the sequence is also equal to 0. Okay, so find the interval of convergence of the infinite series where the terms are x minus a to the n over n factorial. If we apply the ratio test, so the absolute value of a sub n plus 1 over a sub n, we get this, x minus a to the n plus 1 over n plus 1 factorial times n factorial over the absolute value of x minus a to the n. This simplifies to the absolute value of x minus a over n plus 1. And as n goes to infinity, this goes to 0. For all x, where the absolute value of x minus a is less than or equal to d. Okay, so we have a theorem that says if an infinite series converges, then the limit of the sequence is equal to 0. So since we've shown up here this infinite series where the terms are x minus a to the n over n factorial, by the ratio test, this converges for all x, then we have a theorem that says the limit of the sequence x minus the absolute value of x minus a to the n over n factorial goes to 0. Okay, so if we have r sub n of x in absolute value is less than or equal to m over n plus 1 factorial times x minus a to the n plus 1, and x minus a to the n over n factorial goes to 0 as n goes to infinity. Well, the only difference between x minus a to the n over n factorial and the absolute value of x minus a to the n plus 1 over n plus 1 factorial is that they're both from the same sequence. So since this sequence goes to 0, the limit of the absolute value of the remainder is also equal to 0. And since the limit of the absolute value of that sequence is equal to 0, the limit of the remainder sequence is also equal to 0. So this is just a little sketch of a proof for Taylor's inequality. But when applying Taylor's inequality, we use Taylor's inequality to show that a function is equal to its Taylor series at x equals a. So what we want to remember is if we are ever called upon to show that a function is equal to its Taylor series at a, then we have to show that the absolute value of the n plus first derivative is less than or equal to some number capital M for all x values that are within the interval of convergence. So we show this when determining function is equal to its Taylor series. Okay, another thing to remember, the limit of x to the n over n factorial as n goes to infinity, that's equal to 0 for all real numbers x. So remember that. Okay, on the next page, let's see if we can show that the function f of x equals e to the x is equal to its Maclaurin series. Well, we know that the absolute value of the n plus first derivative of f of x equals e to the x. This is just equal to the absolute value of e to the x and this is less than or equal to e to the d for the absolute value of x less than or equal to d. Okay, so in the Taylor's inequality, this is our value of m. So that means the absolute value of the remainder is less than or equal to e to the d times the absolute value of x to the n plus 1. Let's see, let me look. Yeah, over n plus 1 factorial. And we know that the absolute value of x to the n plus 1 over n factorial, n plus 1 factorial, goes to 0 as n goes to infinity. Okay, so e to the x is equal to its Maclaurin series. So now we can write that e to the x is equal to 1 plus x over 1 factorial plus x squared over 2 factorial and so on. And the sigma notation for the Maclaurin series for e to the x is x to the n over n factorial. So who knows, maybe could happen that you'll get a question on a test that says, what's a infinite series for the number e? So you just find the Maclaurin series for e to the x and then replace every x with 1. So you could write it as 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, and so on. All right, next let's find the Maclaurin series for f of x equals cosine of x. So the Maclaurin series for cosine of x is going to be equal to its, let me say that again, the Maclaurin series for cosine of x will be equal to cosine of x, because if f of x is cosine of x, then the absolute value of the n plus first derivative is always less than or equal to 1. So it's bounded. So in the Taylor's inequality, the value of m for cosine of x is 1. Okay, so f of 0 equals cosine of 0 equals 1. The first derivative of cosine is negative sine of x. And then in the Maclaurin series, we evaluate the first derivative at x equals 0, and we get 0. The second derivative of cosine is negative cosine of x. And when we evaluate the second derivative at 0 for the Maclaurin series, we get negative 1. The third derivative of cosine of x, which is the first derivative of negative cosine of x, that's equal to sine of x. Evaluate the third derivative at x equals 0 for the Maclaurin series, we get 0. And let's do one more derivative. The fourth derivative of cosine of x, which is equal to cosine of x. And then the fourth derivative evaluated at 0 is equal to 1. Okay, so cosine of x is equal to its Maclaurin series. The first term, f of 0, equals 1. The next term is 0. And then for n equals 2, we have the second derivative evaluated at 0 is negative 1. So we get negative 1 over 2 factorial times x squared. The next term is 0, so that brings us to the fourth derivative evaluated at 0 is 1 over 4 factorial times x to the fourth. So it will follow this pattern. The next one will be minus 1 over 6 factorial times x to the 6th, then plus 1 over 8 factorial times x to the 8th, and so on. And in sigma notation, you can write it this way. So it's an alternating series. And so we have x to the 2n divided by the quantity 2n factorial. Okay, there's an easy way to find the Maclaurin series for sine of x, and that's just to take the derivatives of cosine of x. But we're out of time for today. We'll start with this one tomorrow. So go ahead and sign in for attendance.